Welcome, NA Physics. Let's talk about the nature of waves. And let's start it off right. Did you hear about the magazine about ceiling fans? You know why it went out of business? I'll reveal that at the end of the video. So we're going to talk waves and sound here today, and we're just getting started. Now, you can remember from earlier in the year that we talked about uniform circular motion, something going around in a circle at constant speed, always changing its velocity towards the center. If we took that uniform circular motion and we made it one-dimensional, whether we shined a light on it and we watched its shadow, or we just looked at the component of the motion, we could get simple harmonic motion, as you can see in the center. And we went on and talked about the pendulum and said that the pendulum was approximately simple harmonic motion. It was definitely periodic. That is, as long as you didn't pull it to the side too far, as long as the amplitude here was 10, 15 degrees at most, you could get a pretty good simple harmonic motion situation. Well, those were similar in that the energy just stays in one place. The energy isn't really able to move out from this object. It's not able to go anywhere. Well, now when we talk waves and sound, we want to talk about the energy being able to leave this vibrating source. So what do I mean when I talk about a wave? I think three definitions are really good for us here. One is a regular rhythmic disturbance in both time and space. Remember, all of these situations, the simple harmonic motion, the uniform circular motion, the pendulum, they were all periodic, meaning that one oscillation took the same amount of time as the next oscillation, and so on and so forth. So those were regular rhythmic disturbances in time. But now that energy is going to be able to leave the vibrating source, and it's also going to be in space. And along those lines, we can say that a wave is a traveling disturbance, not a disturbance that just stays in place like a pendulum or something like that, but it can actually leave the source. And why it's important is it's because it's a way to carry energy from one place to another. Now, here's a really key point. Energy is carried from one place to another, but without displacing matter. I'm going to talk in a second about how you get energy from one place to another with displacing matter, but a wave is important because it's without displacing matter, and that's a crucial difference. I'll talk about that more in just a second. I found this great video online. One of the best things you can do with a treadmill is you can run on it, but look what this fella decided to do. What a great idea. He's got a funnel there that sand can drain out of. And there he has his motion of a pendulum. And see, normally that sand would just fall right underneath the pendulum. But this is not. This is able to leave the vibrating source, and it's able to move away. And so you see maturity of a vibration. It's turning into a wave, which is a way for the energy to leave that vibrating source. So I got some screenshots from another video that I thought were a little bit easier to see. Had that scientist not allowed the pendulum to swing whilst the sand was coming out, you would have seen this picture. And this is just a picture of no disturbances. And I'd like to call this the equilibrium line. It represents maybe a calm puddle or a guitar string that doesn't have any vibration in it. Now, vibration is moving over the same path again and again. And if he had not started the treadmill, but just let the sand trace the same path again and again and again, you would have seen a vibration. Now, you can see amplitude and period in a vibration, and we've talked about that at length in the past. We know that amplitude is how far away from that center you are on either side. And so that's going to be a function of how much work you do, and you're going to see that that is proportional to how much energy the wave is carrying. And so we say we've got the amplitude, this maximum displacement on either side. The period you can't see from a still action, but you saw in the video, it was that time that it took to go all the way over and all the way back. In fact, We covered 4 times the length of the amplitude in one period. Now, you saw in the video what wave shape was made during that time. All of this is to say that waves are caused by vibrations. If you show me a wave, I can show you something that started off as a vibration, but then there was a way for the energy to leave the vibrating source. And so here we have that energy leaving the vibrating source. You can see that in one vibration of the pendulum, this much wave was produced. It swung all the way over and all the way back. And in a period, this much length was covered. And we're going to call that the length of a wave, or a wavelength. Greek letter lambda is going to indicate that for us. We've had periodic motion before. A period, of course, is a time for a complete oscillation. If the waves are equally spaced out in time, like you're going to have when you're attached to a pendulum, or like you're going to have when you're attached to a simple harmonic oscillator, we'll call them periodic waves. They will be waves that are equally spaced out in time, not random. You can see that you can make a wave by doing work in one of 2 directions. You could do work at a right angle to the way that the wave is going to travel. I'll put a V for wave speed. See, this work was done in the Y direction, where that wave speed is in the X direction. That makes this a transverse wave. A particle on the wave is going to move, but it's not going to be displaced after a full cycle. It's going to vibrate up, it's going to vibrate down, but after the disturbance has passed through, it's going to stay where it is. That's that point that I was making earlier about the wave as a way to move energy without moving matter. This coil in this spring is not going to go anywhere. It's going to go up, it's going to go down, but it won't be displaced to the right like the energy is being displaced to the right. Most of those things that I just said are true as well for this longitudinal wave, but do you see how to make the longitudinal wave? You don't work in the Y direction while the wave speed is in the X direction. You work in the X direction. And so you push the coils forward or you pull the coils back. And so you're making areas that can visibly show your work. Whereas here we made this wave crest. Here, when we did work, maybe we would call it in the positive direction. Here we could make these compressed coils. Take a look at something here. The artist did a nice job where they showed these coils very close together versus over here farther apart. That represents high energy right there. And you know what else? There's high energy represented here too, because now we have a stretched region. Sometimes we're going to call this a rarefaction to go along with this compression up here. Those are similar to the crests and troughs that you're used to on a transverse wave. If the work was done in the direction parallel to the wave speed, either forward with the wave speed or completely backward, we call that longitudinal. Remember what I just said about this particle over here not moving anywhere? Well, I could take a representative particle over here. It's not going to move anywhere either. It's going to vibrate forward, it's going to vibrate back, but after a full wave cycle has passed through, it's going to be right where it started. We know the word frequency from our work with other things that were periodic. Frequency is going to be this number of cycles that we have every second. Whenever we have just one disturbance traveling through, we call that a wave pulse, which it's common to see that. And if we have something that's repetitively making wave pulse, wave pulse, wave pulse, that's when we call it a wave. As I said, there are 2 ways to transport energy, and one's particle energy transport, and one of them is wave energy transport. And with particle energy transport, that's like throwing a baseball. Say we had a person standing here and a person over here that was going to catch the baseball. This person could do work on the baseball and apply a force for a displacement, causing a change in the kinetic energy. And that baseball can travel over here, and it can do work on the person catching it. Energy made the trip from left to right, but so did matter. In the end, the baseball is over here. And so the energy was brought Sort of like the Postal Service brings a letter, the energy was brought by the matter, brought by the baseball. That's in contrast to if you had an ability to make a wave. Person over here could do work like we saw in those last pictures, and they could do work on something that they're holding, just like the baseball. But they're not going to let it go. They're going to keep that thing in their hand. Is energy going to move over from left to right? Of course, but matter is not. So matter's involved in both cases. There needs to be continuous matter stretched from source to destination on most kind of waves. Not everyone, but most kinds of waves. We call that matter a medium, the stuff that the wave is passing through. But in the end, the medium isn't going to be displaced. It might vibrate in place, but it's not going to be displaced. Just for you math types, we'll say if we want to see how much energy a wave is carrying, we look at the wave's amplitude. If I ask this person to send down a little bit of energy, they do a little bit of work, a little bit of force coupled with a little bit of displacement. If I told them to send down a lot of energy, they do a lot of work. They would send down a lot of energy by doing more force or more displacement or a combination of both of those. Now say I was able to look at a wave pulse like this top one, and somehow I knew how much energy it was carrying. Maybe this fishing bobber is not just a fishing bobber, maybe it's some sort of sensor that would allow me to know how much energy it was carrying. Say this wave amplitude is 1 unit tall. Make the unit your favorite one. And let's say somehow I know that it was 10 joules of energy that it was carrying. Now, this is a little counterintuitive, and we won't get into all the causes of this, but if I had a wave that was twice as large, a lot of people would guess that it's carrying 20 joules. Turns out, though, this is a direct square relationship, and it would be a 40 joule wave pulse. And so all that is to say that if I had double the amplitude, then I have double, same factor, but squared on the energy. And so if I had this one that was 3 units tall, then that would say that I had blank amount of energy it was carrying. Think of that for a second. Think. Yes, of course. It's 90 joules of energy. How did I get that? I said, well, this is 3 times as big, and so I'm going to have 3 squared times as large for the energy that it was carrying. That's our video for today. Remember that magazine about ceiling fans that went out of business? It was because of low circulation. Thank you.